Hello everyone, my name is Chenghao Wu and I'm a PhD candidate at UCLA working with Professor Henry Burton. Today I want to share with you a recently published article called Modeling Post-Earthquake Functional Recovery of Bridges. So first I want to highlight what we mean by functional recovery. So this is the model that seeks to probabilistically quantify how the bridges progresses through different functionality state over time. Based on the functionality, we may define the complete link closure, partial link closure, and the weight limit of the bridge. So here's a part of motivation of our goal. So as you know, all the bridge in California should be designed based on SDC, seismic design criteria. If you go back to the 2013 version, we only need to evaluate the bridge based on the life safety goal. That means we want to evaluate the bridge based on the 975 year of a written period earthquake. But now in the 2019 version, we not only need to maintain life safety, but also want to make sure the bridge have a short recovery time to return back to normal condition. So there's a one more hazard level added, which is called a functional evaluation earthquake based on the 225-year forwarding period. But one of the limitations is that although cultures now require bridge to be designed based on functional recovery, these requirements are relatively vague, not specific. So part of our goal is to we want to enrich the database, and we really want to build a comprehensive database that will enable designers to design bridges based on functional recovery. So here's our framework. So first you need to look into the hazard of the site, and also you do the damage assessment to get the damage across different bridge components. And based on the damage, you evaluate the functionality state of the bridge. And then we have two temporal variables. One is called impeding factor delay, and the other is called repair durations. The sum of the impeding delay and the repair duration is the recovery time. So here's the limitation is that we don't have an existing database that will enable us to do such functional um, recovery analysis for bridge. So our goal is that we solicit input from domain experts through interviews. So on the one hand side, this is the timeline of how we kind of organize and perform our interviews with domain expert. So this is like spanning from the 2023 November until 2024 September. So we get what we informative information from Caltrans field engineers and officers, and also senior bridge consulting engineer, and also bridge contractor. We get a lot of information, which is very helpful, that include bridge closure and reopening decisions, impeding factor delay and their sequencing, and of course, component repair durations, sequencing, and how they kind of allocate workers to conduct such repair activities. Again, as mentioned before, we need to have a very clear understanding and definition of the functionality state. So based on the possible restrictions that Caltrans will impose for bridge, we define complete link closure, partial link closure, and also weight limit. So based on the recovery progress, we define the two phases. One is called initial response phase, and the other one is called reopening phase. And also we define several possible functionality state that Caltrans may impose to a bridge. And depending on what the phase you are, three of them are only applicable to reopening phase, and both of them are applicable to both initial response phase and also reopening phases. So again, as mentioned before, it's very important to identify and calculate impeding factors. So by meaning of impeding factor, we mean that is delays that will impede the initialization of repair activities. And sometimes it can last even longer than the formal repair of a bridge. So based on our discussion, we kind of identify these six important impeding factors that previously Caltrans undergo in the past earthquakes. So again, we need to have a clear understanding of their sequencing because the time are not linearly added. That means there's some complex interactions between different impeding factors. So following an earthquake, there's a visual inspections, and then they will decide if there's a needed to perform an in-depth inspections. And if yes, they'll perform an in-depth inspection before they make the bridge closure decisions. And if no, they will directly finalize the bridge closure. And then they will decide if it is necessary to trigger an emergency protocol. So by using of emergency protocol, I mean, is that necessary to use emergency funding, and is that necessary to actually accelerate many of the process and it can kind of fasten the repair of the bridge? If the yes, the financing procedure will be waived because they will use the emergency funding to repair the bridge. And also the contract acquisition and design can happen in parallel. And if no, they will kind of return back to the normal condition. That means you will have a long time to waiting for the financing to be approved, and also contractor and design will happen in series. Our second time variable is called repair durations. That means we need to consider how long you spend to repair each of the components of the bridge based on their damage state. So we're using a component level analysis method. That means we're really looking to each of the bridge component damage state and their repair durations. So we need to identify what are the typical components in a regular bridge here in California. So we look into superstructure and substructure and also abutment. So in the superstructure, we look into girder and deck. So for the substructure, we have a column and column foundations. So we have even more components in an abutment, including abutment back wall, bearing, shear K, and abutment foundation. So similar to the sequencing of the impeding factors, not all the component repair will happen at the same time, and we really need to look into the sequencing of how kind of the organize and repair based on the sequencing. So here's a short video showing the sequencing of construction of bridge. The first, you need to insert the column foundation, and then column, and next, this is the bridge girder. And if you look into the abutment, the first is the abutment foundation, and then you need to construct the abutment seat. And next, you're gonna construct the back wall. So here you put this bearing onto the seat. Then here is the bridge girder, and finally you put a deck, and everything is down. So based on this kind of construction sequencing, we define the repair sequencing for components. So here I'm showing the two chains. For the first row, first chain, I'm showing the sequencing for the superstructure and substructures. So for the next chain, this is the repair sequencing for the abutment components. So now I'm going to showing the simple case study to showcase the procedure of our framework. So first step, we have built a detailed 3D bridge model in OpenSys, and we performed hazard analysis to identify the hazard of site. And then we select one of the motions based on the target spectra. And then we performed a nonlinear structure analysis to get the EDP for the bridge components. And here we get the component capacity model. And we combine the response history analysis, EDP distribution, and the capacity. We get a probability distribution for damage state for each of the bridge components. So here's the result in our functional recovery assessment. So first is the probability of entering each of the functional state. Like under each of the hazard level, what's the probability of you have a moderate link closure, extensive link closure, or complete link closure. And here we disaggregate the median time into different factors. So for example, we can disaggregate the time into different impeding factors, like how long you waiting for the approvals and how long you get the financings and so forth. And also we disaggregate our repair durations based on different components. So by doing so, you can identify the most vulnerable disruptors in your components. So finally, here's the distribution of the total recovery durations based on different hazard levels. So with that, thank you for your attention. And for more information, please refer to our full article.